I show here the research octane numbers for the isomers of hexane. Normal hexane has a research octane number RON of 30. 2-methylpentane, the RON is 74.5. 3-methylpentane, the RON is 75.5. 2,2-dimethylbutane, the RON is 94. And for 2,3-dimethylbutane, the RON is 105. The mono and di-branched isomers are preferred as blending components for high-octane gasoline. And in industrial practice, the demand for high-octane gasoline is met by having the alkane isomerization process, in which a feed mixture consisting predominantly of the normal hexane isomer is isomerized in a reactor with a Mordanite or MFI catalyst, and the reactor product consisting of a mixture of hexane isomers is separated using LTA5A zeolite that essentially sieves out the linear isomer, and the linear isomer is recycled back to the reactor. The raffinate phase consisting of the monobranched isomers 2MP, 3MP, and the dibranched isomers 2,2-DMB and 2,3-DMB are incorporated into the gasoline pool. I discuss in this presentation an alternative to this conventional alkane isomerization process, in which both the reaction and separation steps are combined into a single unit with MFI catalyst. Let's see how that works. In order to appreciate the use of MFI zeolite both as a catalyst and as a separation agent for the alkane isomerization process, let us examine the unary isotherms of normal hexane, 3-methylpentane, and 2,2-dimethylbutane in MFI zeolite at a temperature of 362 Kelvin. These are the configuration bias Monte Carlo simulations for the unary isotherms. The red circles are for normal hexane, the blue squares are for 3-methylpentane, and the green triangles are for 2,2-dimethylbutane. We see that the normal hexane has a saturation capacity of about 8 molecules per unit cell, whereas the mono and di-branched isomers, the saturation capacity is approximately 4 molecules per unit cell. To understand these differences, let us look at snapshots showing the location of NC6, 3MP, and 2,2-DMB within the straight and zigzag channels of MFI zeolite. Normal hexane can align itself either along the straight channels and or along the zigzag channels with equal ease, and the saturation capacity is 8 molecules per unit cell, because the length of a normal hexane molecule is equivalent to the distance between two adjoining intersection sites. 3-methylpentane, the monobranched isomers, prefers to locate at the intersections, and there are 4 intersection sites per unit cell, and therefore the saturation capacity is limited to 4 molecules of 3 MP per unit cell. The same holds for 2,2-dimethylbutane, which also prefers to locate at the channel intersections. And since there are 4 intersection sites per unit cell, the saturation capacity is limited to 4 molecules of 2,2-DMB per unit cell. Here are configuration bias Monte Carlo simulations for mixture adsorption for an equimolar mixture in the gas phase consisting of normal hexane, 3-methylpentane, and 2,2-dimethylbutane. We see that with increasing bulk fluid phase fugacity, this is the total fugacity of the gas mixture, the adsorption gets increasingly in favor of the normal isomer because of entropy effects that favor normal hexane that has the higher saturation capacity. Both monobranched isomer 3MP and 2,2-dimethylbutane, the dibranched isomer, are entropically challenged, and due to the entropic penalty, they lose the battle for occupying vacant sites with increasing bulk fluid phase fugacity. And at post-saturation, the mixture adsorption is almost completely in favor of the normal isomer. Watch also my presentation, Packing Effects in Mixture Separations, on my YouTube channel. So the message that emerges here is that the mixture adsorption favors the linear isomer, and the monobranched and dibranched isomers are entropically challenged. Let's examine intracrystalline diffusivities of the hexane isomers. Within the intersecting channel structures of MFI zeolite, the channel dimensions are 5.5 angstrom in size, and the normal hexane is less strongly confined within these channels than the monobranched and dibranched isomers, and the diffusivities decrease by 1 to 2 orders of magnitude with increased degree of branching. Therefore, the intracrystalline diffusion favors the linear isomer and disfavors the monobranched and dibranched isomers. Now, with this background on mixture adsorption and intracrystalline diffusion, let us proceed to examine how a isomerization reactor will work for the alkane isomerization process. And in this reactor, we use MFI catalyst. In order to demonstrate the technological benefits of the synergy between adsorption and diffusion, we simulate the transient operation of a fixed bed reactor packed with MFI catalyst, carrying out the isomerization reaction. We keep matters simple and consider 3 components. Component 1 is normal hexane, component 2 is 3-methylpentane, and component 3 is 2,2-dimethylbutane. We have a reversible reaction of the isomerization of NC6 to 3MP, with a reaction rate constant R sub 1 and the isomerization of 3-MP to produce 2,2-dimethylbutane with a reaction rate R sub 2. Both these reactions are reversible, and we assume that these reaction rates are linearly proportional to the molar loadings Q1, Q2, and Q3 of components 1, 2, and 3. The forward reaction rate Kf1 is assumed to be 0.01. The backward reaction is taken to be a factor 2.5 times lower than the forward reaction rate constant. The same holds for the isomerization reaction of 3-methylpentane to 2,2-dimethylbutane. We take the forward reaction rate constant to be 0.01 per second, and the backward reaction rate constant is a factor 2.5 times lower than the forward reaction rate constant. Based on the information on the intracrystalline diffusivities presented in the foregoing slide, we take the ratios of the Maxwell-Stefan diffusivity to the square of the crystallite radius to be 2 times 10⁻⁴ per second for NC6, 2 times 10⁻⁵ for 3MP, and 1 times 10⁻⁵ for 2,2-dimethylbutane. We simulate a fixed bed catalytic reactor with inlet partial pressures of components 1, 2, and 3 equal to 16 kilopascal for normal hexane, 0.2 kilopascal for 3-methylpentane, and 0.2 kilopascal for 2,2-dimethylbutane. The simulation methodology is described in detail in my paper in Reaction Chemistry and Engineering 2017, and I refer you to this paper for details of the numerical solution to the partial differential equations describing adsorption, diffusion, and chemical reaction in the fixed bed catalytic reactor. Let's now focus on the simulation results for these set of input data. The simulation results are summarized in these two graphs. The graph on the left shows the steady state concentration profiles along the length of the fixed bed catalytic reactor for NC6 marked red, 3MP marked blue, and 2,2-DMB marked green. Rather than use the reactor length as x-axis, I use the mass of the catalyst in kilograms divided by the molar flow rate of the feed mixture, the inlet F sub naught, in units of moles per hour. So the units of the x-axis are kilogram per mole times hour. This is linearly related to the length of the fixed bed catalytic reactor. If we wait for steady state to be achieved, the concentrations of the 3 components leaving the reactor are shown here. We have about 1 mole per cubic meter of NC6 and about 2 moles per cubic meter each of 3-methylpentane and 2,2-dimethylbutane. The advantages of the adsorption-diffusion synergy is best exploited by transient operations, and the graph on the right hand side shows the gas concentration exiting the fixed bed catalytic reactor as a function of time. Rather than use time as the x-axis, I use a modified time parameter where the time t is multiplied by the molar flow rate at the inlet, F sub naught, and the F naught times T is divided by the mass of catalyst in the bed. We note that during this time interval between, as shown here, say less than 0.5 moles per kilogram, the components exiting the bed consist exclusively of the branched isomers, green 2,2-dimethylbutane and blue 3-methylpentane, and practically none of the normal hexane exits the bed at this time. And therefore, if we terminate the operations and recover the products at this time, then we will have the desired di-branched isomers 2,2-DMB and the monobranched 3MP as products. And this obviates the need for a separate separation step. In order to appreciate the transient operation, I also show here the development of the molar concentrations as the components react and the concentration fronts traverse the length of the fixed bed catalytic reactor. I plot here the molar concentrations of the three components, NC6, 3MP, and 2,2-DMB, using the same color code here. And let's first run through the simulations quickly. Red is NC6, and red, that is NC6, gets progressively converted to produce 3MP and 2,2-DMB, and at steady state they will have the concentration profiles as shown here in the top left-hand graph. But the advantages of transient operation is best demonstrated by running the reactor Let's see how the concentrations develop. At this stage, none of the products has left the reactor, and the first product to leave the reactor is the green product, which is 2,2-DMB. 3MP has not yet left the reactor. The concentrations of 2,2-DMB is the highest in the gas phase for two reasons. Because one, it's being formed by isomerization of 3MP, and 3MP is formed by isomerization of normal hexane. And furthermore, the diffusivity within the crystallites of the branched isomers are significantly lower than that of the normal hexane, and therefore the branched isomers are predominantly present in the gas phase. At this stage, no 3MP has left the reactor, and which is the blue line, and we see at this stage 3MP starts to leave the reactor. No normal hexane has managed to reach the exit of the fixed bed at this stage of the transients. And if we stop the operations here, the products are predominantly blue 3MP and green 2,2-DMB. So we do not need a separate separation step if we stop the transient operations at this stage. If we continue and allow steady state to achieve or develop, then normal hexane will also leave the fixed bed, and the advantages of transient operation cannot be exploited. So I leave it there.